Good morning. My name is David Griffith, and I'm here representing the Wastewater Treatment Incorporated Group. And the name of our project is the treatment of wastewater using polymeric sorbents. You'll see I have two samples of the sorbents that we use going around the room that you guys can look at during the presentation. Here's our abstract, which you can find on our website and has been distributed to today's judges. My team consists of David Baginski, Luis Perez, Maya Robinson, and myself. Our faculty advisor is Dr. Judy Zhang, and we were helped by Anthony Shields, a graduate assistant. Motivation. The problem our system is looking to correct is contaminants of emerging concern. Emerging contaminants include a wide gamut of chemicals, including pesticides, pharmaceutical and personal care products, as well as steroids and hormones. These chemicals have all been identified by the EPA as either harmful or potentially harmful to the environment. The problem, however, is a lot of the current methods are either inconsistent or very expensive at removing these emerging contaminants. For instance, activated carbon has proven to have some success with different emerging contaminants, but its high regeneration costs and high attrition rates make it very expensive. Whereas chlorination and membrane bioreactor systems have been ineffective and inconsistent on different emerging contaminants. Our proposed solution is polymeric sorbent resins. The reason we picked resins is because of their high absorption rates due to their large surface areas, as well as easy desorption due to their weak bonds with the contaminants, as well as their inexpensive regeneration. Here's our project overview. You see we began with local wastewater that we collected, ran it through total organic carbon testing, and then created synthetic wastewaters when necessary. We also added phenol, 3-nitrophenol, and 4-chlorophenol to our treatment column and ran it through either Amberlite XAD4 or Amberlite XAD7. We then ran the system through either adsorption or desorption and were left with a treated effluent. Our technical design constraints included removal efficiency, regeneration, flow rate, attrition, and solution chemistry. Two of the main technical constraints that we focused on were removal efficiency and regeneration, meaning that our system had to effectively remove 95% of the contaminants for the prescribed time, and the system also had to be able to retain that 95% removal over at least 10 cycles. Our non-technical constraints included cost, column dimensions, laboratory safety, sustainability, and energy efficiency. Again, two of the main ones here are column dimensions because of the physical limitations of our system, as well as energy efficiency because we wanted to make sure our system was running at lower levels compared to other industry standards. Here's an outline of the wastewater effluent system at the Southeast Wastewater Treatment Plant here in Philadelphia. The wastewater begins being collected and runs through screening and grit removal. Then it goes through primary treatment of primary sedimentation, as well as secondary treatment of aeration and biological reduction. After the final sedimentation and secondary treatments are done, is where we plan to implement our tertiary treatment. This is also where we collected our local wastewater sample. The two resins that we use in our system are Amberlite XAD4 and Amberlite XAD7. Amberlite XAD4 prefers hydrophobic interactions, while Amberlite XAD7 prefers hydrophilic interactions. These two differences become important when we look at the efficiencies of these two Amberlites later on in the discussion. The contaminants we used were phenol, 3-nitrophenol, and 4-chlorophenol. We use these contaminants because they have very similar molecular structures to some of the emerging contaminants being found in the world today, as well as they are very common and easily accessible in the laboratory. Before looking at the efficiency of our system, we had to analyze exactly what was in our wastewater. So two of the things we had to look at were organic carbons in the system as well as inorganic compounds in the system. At the beginning of our testing, we expected to see total organic carbon levels of 80 to 290 milligrams per liter. However, after performing total organic carbon testing, we see that our average concentration was only 42.4 milligrams per liter. This means that after secondary treatment at this plant, our wastewater effluent, which is the effluent to our system, is actually relatively clean for wastewater standards. In terms of inorganic compounds, however, we expected our system to be moderately hard and to contain 220 milligrams per liter of inorganic compounds. After performing our testing, however, we noticed that our average inorganic compounds do in fact meet that requirement. So with this information, we know exactly what's in our wastewater, or we have a general idea of what's in our wastewater, and we need to look at the effects of the inorganic and organic compounds in our system on our system's efficiency. The way we tested this was by running our resins through running our resins through DI water and different variations all the way to 100% wastewater concentration. As you can see, the effectiveness decreases when you go from DI water to wastewater by 19.3%. This means that even though the compounds were relatively low on our wastewater, it still has a very large effect on our system. Attrition. When running our tests, we had to make sure that our system didn't lose more than 1% of the resin mass. The reason for this is we need to keep attrition rates low for cost, as well as make sure that our resin doesn't end up in our effluent source. After our first attrition test, we saw that the percent retained was only 91%, which was drastically lower than the required 99% retention. However, we completed 2 more attrition tests that where our resin ran for 5 cycles and 1 cycle. In both of these tests, our resin retained adequate levels to meet our attrition levels. The reason for the 91.3% is because we measured the sample a little wrong. When we first did our attrition test, we collected the resin sample, as you can see over there, and we poured out the water on top of the resin and measured the resin left. On the second 2 tests, however, instead of pouring out the water on top, we let the resin sit and let the water evaporate out and then measured the resin afterwards. We believe that by pouring out the water, we actually lost some of our resin mass that was still circulating in the water, and that's where a lot of our mass left. We also tested removal efficiency. We had to make sure that all of the contaminants that were being adsorbed by our system were also being desorbed through our desorption processes. We saw that our average desorption efficiency was 94.6%, which if you take out the first 2 tests, which were run at wrong flow rates, increases all the way to 98.7%. The primary system parameter is the optimal flow rate. Obviously, the slower you run our system, the more efficiently our system will adsorb contaminants. However, the slower your flow rate, the larger your reactor size has to be. So we saw that the curve starts to level out between the 6 to 6.5 range. We ran a number of tests and came to the conclusion that our optimal flow rate that we would go with were 6.3 bed volumes per hour. We use this optimal flow rate as well as because of the size limitations, as I stated, as well as the flattening of the curve. Here you can see an outline of the Southeast Wastewater Treatment Plant that gives you a better idea of the size limitations we are dealing with in our project. It is 120 feet north-south on this graph, as well as 350 feet east-west on this graph. Based on our optimal flow rate, our diameter-height ratio, and our size limitation, as well as our 90 million gallons per day load, we propose 12 reactors in parallel, including a total cross-sectional area of 3,800 square feet. As I stated, the third parameter in this conclusion was the diameter-to-height ratio. In this testing, we looked at 0.26 ratio, 0.13 ratio, and 0.09 ratio. You can see that although we doubled the surface area, between 0.26 and 0.13, and then increased it significantly between 0.13 and 0.09, the breakthrough numbers don't increase at significant enough levels. This means that although the diameter-to-height ratio does affect our system, it is not as important to overall rates as the optimal flow rate is. Also, we tested the efficiency of X87 versus X84. As you can see, the breakthrough point for X87 is 21.6, while the breakthrough point for X84 is more than double that at 50.1. The reason for this large disparity is the fact that X87 prefers hydrophilic interactions. Because of this, essentially the H2O compounds in our wastewater become interferent compounds, so to speak, and take up valuable space on the surface area of the X87. This accounts for the large difference between the two. The last parameter that we wanted to make sure was the cost efficiency. We looked at electricity costs, specifically dealing with regeneration. We saw that for activated carbon, the regeneration cost is 0.67 kilowatt hours per kilogram, while for our system, the cost for regeneration was only 0.28 kilowatt hours per kilogram of resin. This means that we have about a 58% reduction in electricity costs in terms of regeneration. Furthermore, for operating costs, we saw that the cost of methanol was 10 cents per cubic meter, and our total operating cost for our system was 12 cents per cubic meter, while that for activated carbon is 15 cents per cubic meter, showing that we still have a 20% reduction in operating costs. Here is a cost and project budget sheet, which you can also find on our website, showing that many of the items we used were donated by Clean Water Ventures as well as Dr. Zhang. Also, here's our schedule and experimentation, where you can see some of the recent experiments we performed in this section. Technical challenges. We had many technical challenges with this project, but two of the ones that kept resurfacing were limitation in instrumentation as well as bacteria growth. When we were filtering our system, on multiple occasions we would have filtered at least a liter and then go back and find out that we had bacteria growth in our system, which means we had to refilter it. Also, there's an occasion here you can see where we had clogging in our resin column due to bacteria growth in the column. When your column clogs with bacteria, it actually lowers the efficiency rate, which can affect, obviously, our whole system design. Summary. So far in Senior Design 2, we have determined operating and regeneration costs, determined optimal flow rate, and determined optimal diameter to height ratio. The only thing left to do is to complete our multi-contaminant removal efficiency testing. Acknowledgements. We'd like to acknowledge Dr. Judy Zhang, our advisor, Mr. Ruzbe Tarani, Dr. Robert Ryan, Mr. Thomas Ferguson, Drew Brown, and as well as the rest of the members of the Southeast Wastewater Treatment Plant and Temple University. Here are some of our references. Any questions? Sorry.
Questions? You're good.
You don't have any?
Oh, I didn't say
Oh, I was about to say. I was confused.
So, when you looked at the full scale, the scale up to the
Yes.
treatment plant size, I think you said you needed 3,800 square foot. You needed 12 reactors and, I don't know, 3,800 square feet.
That's what we
The
designed
total
for, yes.
area was 38. So each reactor was 20 feet in diameter.
Yes.
How is this larger size going to affect the wall effects? So you've got this very tiny reactor you're working in the lab. You're going to scale it up to something that's 20 foot in diameter. What's that going to do to the wall effects?
Well, obviously, we would have, in terms of scaling up, the ratio of surface area on the wall would be a lot smaller on this large reactor. So this might end up making our system slightly less efficient, but when we look at the numbers as well as other scale-ups that people have used, we used a formula that we believe should counteract some of that loss.
So you think by scaling them up with the smaller wall ratio, it's going to reduce the efficiency of the system or increase the efficiency of the system?
When we have our system, once our surface area to contact time with the contaminants in our wastewater to our resin is what we were looking to optimize. So when we were scaling up, we looked to use a formula that would make sure that it includes all the contact time that our system needs and would effectively give us our desired 90 million gallons per day while retaining all of our design parameters. So I don't know if that answers what you're asking.
Well, I'm thinking of wall effects. I mean, you've got water water flowing between your resin and the wall.
Yes.
And you said that your lab scale, the ratio of the wall to the volume is much larger than you would have in a full scale.
Yes.
And so would that increase or decrease the potential for short circuiting along the walls?
I feel like it would decrease it.
Okay, so if you have less short circuiting, is your treatment efficiency going to increase or decrease?
My treatment efficiency with less short circuiting should increase.
Okay.
Yes.
All right.